I'm only going to talk about the aspects that are relevant for HPC. So it'll mainly be looking at structures like loops, conditionals, and other features that are relevant for the HPC space. So just to give a general overview of what we'll discuss today, and please stop me if you do have any questions, or we can discuss them at the end. I'm going to introduce some general kind of assembly type instructions that are available on ARM architectures. I'll introduce the vector registers that are available now on current ARM hardware, and then I'll talk more about the what I briefly discussed in previous talks was SVE, or the Scalable Vector Extension. So I'll introduce this idea with some examples, just an overview of what registers are involved, and then I'll talk more about this idea of vector length agnostic programming. That's the idea when the software view doesn't see the size of the vector registers. So that's a concept which I'll cover in more detail. And then finally, I'll end off by giving some more examples of some assembly type instructions and how to program the vector length agnostic approach using SVE. So that will be with, as I said, like assembly type instructions and intrinsics. So to start off with, and this kind of builds on what the ARM instruction set looks like in terms of assembly type instructions and what registers are involved. So the ARM instruction set, please bear in mind that we have a fixed vector size of 128 bits for this. So it's also called neon. So when you hear me talk about neon vectorization, it's a 128-bit fixed vector register size. Now, the other thing to bear in mind is that the word size, even though we have a, you've heard of AArch64 or ARMv8A, ARMv8 point something A as the underlying instruction set architecture. Even though it's 64-bit addressable, the instructions are still based on a reduced instruction set type arrangement. So they're 32-bit. So we have storage for 32 bits with instructions. But in terms of the 64-bit general purpose registers, we have 31 of those. For each of those, it can be represented in either as two, you can have it as two 32-bit registers, which we call W registers, or we can have the full register occupied as a 64-bit X-type register. Now, the X register is kind of important to remember because I'll be talking about that later on during the talk. So a couple of key things here that a word size is 32 bits and the X register is 64 bits. And whenever we have a W register in an X register, it's the lower half of the register, the X register, which represents the values for the W register. Similarly, we also have 32 128-bit floating point registers available. And just like with the the 64-bit registers, the 31 of those, here we have up to 128 bits. So for if we're only using the double precision type D registers, then 64 of those bits will be represented in a 128-bit queue register. Again, at the lower, using this 128-bit register here, it will be the lower part of the register where the D values are represented. Now, I'd just like to say not too much about it, but in terms of how vector instructions operate with the ARM Neon vector extension, basically, if we take a quick example here, we have an addition of two vector registers. It's just a simple instruction, FADD, and it's just adding these two operands and storing the result into the first one. So it looks something like this in terms of operation. So what's happening here is that we have the two vector registers, the 228-bit registers, Q0 and Q1, and we've effectively loaded these up into vector registers, and within each vector register there are four what we call lanes. This is because here we're representing single precision values of data. So if this had been if the S had been replaced with a D, if it was double, we would only have two lanes, because each of the doubles would be represented by 64 bits. Here, you know, single precision, we have 32-bit representation, so we can fully pack four of those in one 128-bit size vector register. That gives us four vector lanes. So what happens when the operation executes is that these four lanes acted upon by the addition, and the result is then stored back into the original Q0 register. But the key concept here to note is the idea of a lane. So you have, because of the size of data, so you have 32-bit size data, but you're fitting that into a 128-bit vector. You know, you can do that 4 times in a fully packed way. So we have these 4 lanes. Just to go, you know, give a more general idea of what's going on. So the instruction was FADD. It's just one of the instructions that's available in the ARM ISA, and it's just saying to add 2 operands and store the result back in vector registers. And in a more simplistic view, it's this kind of thing. So it's just adding a single precision, adding values, floating point values to itself. Now, just to go into a little bit more detail, and if you're not familiar with assembly, don't worry too much about this, because it's not really about the assembly, it's about how the assembly is structured, rather than what I wouldn't worry too much about what each individual instruction is actually doing, but it's the concept of the structure here, the loops. So what we're actually looking at here is a simple, in C, we've got this loop. So it's just looping over some floating points, you know, with a 32-bit representation. And the thing to note is that at runtime and compile time, we don't know the size of n. So if the compiler was generating this assembly language, it wouldn't know the value of n. And that's the key concept, because obviously if the compiler knew the value of n, it would be able to generate more accurate assembly language. So we don't know what n is. So the compiler is going to generate something like this in terms of assembly. And what this is doing is that because you have fixed size vector registers of 128 bits, and the data that we're looking at here is of size 32 bits. So you have single precision data stored in this array here, A. What the compiler can do is recognize that it will need to load up 8 of these values to fill a vector register. So it can generate the assembly to do that. But it has to take into account, the compiler needs to take into account that you're looking at chunks of size 8 because of the vector, the vector register, and how many of these single precision values you can fit within that register. So you need to account for several situations. You need to think of when n is, say, 8, when you just do one loop of the iteration, one iteration of the loop, or you need to account for when there are less than 8 values, when you don't actually do the loop and you do something else, or then you need to account for when there are more than 8 values, but n is not a multiple of 8. So you could be doing one iteration of the loop, and then you might be doing some of the remainder operations. So all this has to be coded up into assembly, and this is kind of what you would do for any if you run any architecture, different language, slightly different, you would do the same kind of thing, because you have fixed vector length for your your vector registers, and the compiler only knows about those. So that's the key thing to note here, that you have to do a main loop, and you're going to go over that loop, filling the 8 single precision values into two vector registers. Here we're going to call them V0 and V1. And I should also say as well at this point that the ARM architecture is a load store type architecture. So there are no operations where you can go directly to main memory or something like that. You have to load everything into these registers, work from those, and then store back the result. So it's a load store architecture. And that's basically what this loop is doing here, and it's checking that it's checking for when there are more than or 8 iterations left of the loop. So it's taking account of the number of iterations that is actually done. It's comparing that with the value of n that is whatever that is. And if that is, if it's a multiple of 8, or if there are less than 8, then it's going to do something else. So when it can't do this loop anymore, it's either going to decide, and it's going to this here is to say branch if a particular register has generated a certain state. So otherwise it's going to go back to the loop and repeat. But if it does come out of the loop, then it's going to do what we call a drain loop, or it's going to attempt to do a drain loop. And what the drain loop does is to work on any remainder of these single precision 32-bit scalar values that are left, if there are any. and it's going to do the same operation, but in scalar. So instead of doing the vector FADD, it will do the scalar type FADD on these 32-bit single precision values, and essentially it's doing the same operations, but it's kind of, the whole assembly is kind of getting messy because we have this main loop for unrolling, something going on here, and then potentially if this is if these conditions are met, it will do this drain loop. So there's quite a lot going on, and that's just for this loop. So that's the thing to bear in mind here, that we have a main loop and a drain loop. Now, as I've mentioned before, we don't really program in assembly. We would use a compiler. We would look at our high-level source, C, C++, Fortran, and then let the compiler do all the work, generate the assembly, which is fine. That's great. We're just looking here at what's going on under the covers. So another way of using kind of ensuring or getting a finer grip on your code is to you can use assembly, inline assembly, or you can use what are known as intrinsics. We have what's known as the ARM C language extensions. So you can include these as a header file, and what they do is give you access to some predefined types and functions that are termed intrinsics, that actually represent some of the assembly that we've just, or type of assembly that we've seen. So it's a higher level than using assembly to achieve the same results. And this is just what it looks like. We can compare that with what we were doing before, but this is essentially generating your main loop and your drain loop and all those conditions that we saw previously. But it's just doing exactly the same, it's just doing that loop. Okay. And as I've said, we don't really all want to go into hand-coded assembly. Compilers are there to do this job for us, but the reason I've covered this is to go over what's happening, or if you want more control over generating optimized loops or that kind of thing, then you can look at assembly, or you can look at intrinsics. I mean, the compilers will generate assembly output if you want to look at it. And the key thing to note is the way the loop was structured in terms of assembly, with the drain loop. That's the key thing to note here. And as I mentioned before, the most of the optimized maths libraries do have some kind of hand-tuned code in there, so they ensure that there are optimized loop structures and that kind of thing. So that's another application where this kind of thing is used. In terms of limitations, so as I've said, most of the current ARM architectures are they only have 128-bit size vector registers. That's the what I mentioned before, the Marvell Thunder X2 chip, the Amazon AWS Graviton 2, the Ampere Ultra. They're all with 128-bit size fixed vector registers. Now, the next step really is what is coming next in ARM architectures, and that is to make the capability for larger vectors. But the way we go about this is not to have the same approach as with the neon type vectorization. So we're going to introduce shortly the scalable vector extension, and I'll talk more about that, and it will all become more clear as to why it is more powerful than having a fixed size vector approach to use. So in terms of just as a general overview of what the scalable vector extension is, it's the idea of vector length agnostic programming, and what this means is that it's a hardware implementation choice. So it's not something that you consider at the software level. So if you have the vector length is defined. What we do in SVE is allow from 128 bits up to 248 bit size vector registers. Now, you can imagine that the 2048 size wide vectors are quite large. They're going to be quite big, and you would perhaps have to do a lot of work to fill those vectors. So they may not be applicable to your workload. But essentially, this vector length will be defined by the hardware. Now, what this idea allows us to do is effectively, if you wanted to, you could compile your code on one SVE for one SVE hardware, and it would run on any other, irrespective of the size of the vectors. And we'll see later, but one reason for that is that the compiler will not generate code for a fixed vector register size as it would do for ARM Neon. It will generate vector length agnostic type code, and we'll look at that in more detail. But it's this key idea that's important really here. The other thing to note is that SVE, it's not just adding, it's not just a step from Neon then. It's a whole different idea of implementing vectors. That's another key thing to note here, because of this agnostic approach. Sorry, the vector length agnostic approach. And in doing this, what SVE enables us to have is that we have more control over kind of structures and how we would represent a loop, and also a lot more over dependencies and things like that. So you'll see as we progress, it is a very powerful idea of programming vectors. As a general overview, basically we have the hardware sets the vector length. As I've said, in software, we're not thinking about the length of the vectors, and you know, we could run the same binary on a 5112-bit vector machine or a 256-bit vector machine. It should just run the same way. Obviously, in terms of performance, there will be differences, but in terms of the code running, it should work. And what SVE does in terms of vectorization is it gives us these new features. So we have better gather, load, scatter, store operations. These enable more efficient ways of both fetching data from memory into registers, and similarly writing it back. We have this idea, we're going to talk a lot about predication shortly. So each lane of the vector register can be acted upon by a value in a predicate register. And this is very powerful because it enables us to look at different size data structures, data types. It allows us to write more elegant assembly type code as well, and a lot more power in that. Similarly, there's more control over speculation and that kind of thing in a loop. So it's all, you get a lot of extra features with SVE. So to give an overview in terms of, I kind of guess a general overview, how do you compare SVE to a traditional type instruction set architecture that has a fixed vector size? Well, say we want to compute data that has, you've got 10 chunks of 4-byte data, and the key to remember is that it's data of size 4 bytes. So you're working with 4 bytes. So 32-bit 4 bytes. So at the basic level, if you were looking at the AArch64 ARM v8a architecture, you could do, if you were doing a loop, you could do 10 iterations over a 4-byte register. So you could just load the data up into each one of your chunks of 4 bytes, load that up into a 4-byte register and do that 10 times. So there are your 10 classes. Now, if we move on to what we discussed earlier, the neon type vector approach with the 128-bit wide fixed vector registers. So, we have there, a 16-byte wide register, and we can fit 4 of these 4-byte chunks of data into one of these 16-byte vector registers. So we can do that 2 times, basically. So we can fit 4 into that glass and 4 into that one. And what this does is then enable us to do the loop just twice using a vectorization. So this is kind of what we saw in the assembly language at the beginning with the neon assembly. It was doing a main loop, and then it was doing this drain loop. Now the drain loop here comes in because you've used up basically at this point you've used up 8 of your 4 bytes of chunks of data, but you have 2 remaining. So you can only use here 32-bit registers, so you need to do 2 more iterations. And in each of the iteration, you're obviously filling in one of these 4-byte chunks of data. That's how it works in your fixed vector type approach. Now, how does it look in SVE, the scalable vector type approach? Well, here, let's consider that if we have, again, a 128-bit wide vector that's been set by the hardware, but it's vector length agnostic. So the compiler will generate the code, the assembly, differently to what it would do here. And in doing that, we can do what we did here. We can fill the 2 128-bit wide vectors twice and do a loop, but we can also do the same loop a 3rd time. But for the 3rd iteration, we're only going to half fill it, which is fine because it's vector length agnostic. Now, don't worry too much about how this operates, but the key thing to note is that we've done the same loop just 3 times, but due to operations instructions, with vector length agnostic approach, this is possible. It's not possible here with a fixed vector size, and we'll see in more detail why this is possible. But it boils down to the fact that we're using predication and predicates. So it's actually it'll actually be the predicate that controls the data coming into the loop. And as I mentioned before, that in terms of how big a vector can be for SVE, anything from 128 bits up to 248. And the key thing to bear in mind here is that we have this idea of a vector length, which is this, but the vector length will be defined by len times 128. So when we think of len, if the vector length is 128, len will be 1, obviously. But if the vector length is 5112, then the vector length will be 4, and so on. But essentially, it's len will be the number of multiples of the 128-bit size that we discussed before. As I mentioned before, that I've introduced the idea of per lane predication. This kind of thing we'll see in more detail later, but this is how you can add two vectors with SVE using a vector length agnostic approach. Basically, you have this predicate register which will have zeros and ones in positions that are either they'll be active or inactive lanes, and where there is a the way the vector operation will work is it will have input from this predicate, and it will do something on this lane based on the value of the predicate. So either it will be if it's an inactive lane, it won't do anything. If it's active, it will, in this case, add. And similarly, we can use a related approach in terms of predicates for loop control. So we can have a vector instruction for loop control that will have a predicate input, and it will be looking at two bounds of the operands, the lower and the upper value of the loop, and basically if the counter is less than the upper bound, then we can do something on the loop. We can do something on the register based on this predicate register, or not, depending on if the lane is active or not. But we'll cover this in an example in more detail later. So to just give a general overview in terms of what vectors we have. So we have 32. Now they're going to be called Z registers. So when you see Z register in SVE assembly, you'll know that it's a vector register. And as I mentioned, the size will be defined by this len idea, which will be the number of multiples of 128 bits that fit within the actual hardware-defined vector length, or VL. And the interesting thing here to note is that you can store you can store different types of elements in these vector registers, half precision, single precision, double precision. And we couldn't do that before. We've also got 16 predicate registers now as well. So those are P registers. So whenever you see a P register in the assembly, it will be a predicate register, and it will obviously be different to the Z vector register. So basically, for SVE, the main registers are P registers, predicate, Z vectors, and the double precision X type register comes up a lot as well. You've also got a first fault register, which is for software speculation. So you can interrogate that it will have a value based on whether or not a particular condition has happened, but we'll cover that later as well. So this is just to give you a general idea of what a vector register or sorry, SVE register looks like. So as I mentioned, they can hold either packed or unpacked representations of data. Now, for this example, please note that the VL is 256 bits. So we have a vector length of 256 bits. So the hardware here, the theoretical hardware, whatever it is, would have 256 bit wide vectors. And this is how we could represent, using one of the SVE registers, the Z registers, this is how we could represent 64-bit type data. Now, the key thing to note here is for a predicate register, which is 32 bits, because we have because len will be 4 here. We have 4 lanes for this type of data, and it's only the first bit in each one of those lanes that is actually relevant for the predicate register. So you don't need to worry about any of the others in this case. So only the first bit will be relevant. The others will be ignored. Yeah. So again, this is the same, but this is for if you had single precision 32-bit type representation. Now you've got 8 lanes, so you need 8 bits in your predicate register. Again, the other bits are ignored. Finally, what happens when you have these are both for packed data. So you're filling the register completely. Now, what happens if you have irregularly spaced or unpacked data in your vector register? Because you've got a large vector register, 256 bits, but you're only representing 32 bits of data. So here we've spaced it out, and we have a representation again with your predicate register, but the predicate register looks like in the first case when you have 64 bits. So these are interesting because that single predicate register can control both representations. Now this is important and relevant when you have types of mixed data types in your code. But don't worry too much about this idea. It's just the idea of having only the first bit is relevant in the predicate register, depending on the size of your data representation. So in terms of how you can, condition flags in SVE, they're very similar to what we have in the AART64, but some differences. But you can use them. The main point here is that you can use them just like you can in ARMv8A. To control branches, conditions, and so forth. So you'll see things like B dot something, maybe B dot kind of MI or B dot eq, that kind of thing. But it's just checking a condition flag, usually to make an action around a loop. And we now have just to recap what we've covered, we now have the ingredients to consider SVE in more detail. And also kind of what vector length agnostic code is going to look like. So we can grab data from non-contiguous memory locations because of the predication, and we've also got essentially you can use better floating point type operations for any reductions because and that kind of operation, because you've got predication, so you can do the operation in fewer cycles of the CPU and making it faster. And it's also useful in terms of accuracy as well. This if you're looking at bit repeatability, then with because of the way the operations are performed in the same order, rather than at compile time or something like that, then you're guaranteed repeatability in terms of numerical accuracy. So I'm just going to talk about vector length agnostic programming again, just go over and kind of recap what we've already covered, just because it is quite a lot to take in. But once it kind of becomes clear, then it's very clear and it all makes sense. So the main idea with vector length agnostic programming is that you write your source code, your C++, C, Fortran, you compile it somewhere, and then you can run it on any hardware that supports vector length agnostic type vectors like SVE. And what this type of programming allows us to do is that it allows us to more easily vectorize loops that wouldn't be as vectorizable if you had if you were using a more conventional type of vectorization with fixed size vectors that you know about, and that kind of thing. So you get more loop control. You also have the ability to vectorize pieces of code that wouldn't vectorize before as well, which is also great for performance. In terms of how this is supported in the community, so it's been around since around, well, the last 5 years or so, and since then, both ARM and the open source community have been working together to get a lot of the improvements into the community. We've done this through GNU, GCC, LLVM. We've also done it through emulators as well, like QEMU. Debugging applications have also been made aware of SVE, and we constantly upstream knowledge and developments to the open source communities of LLVM, Linux kernel developers, and GCC. On this note, I should just add as well that there is only currently available one ARM architecture or piece of hardware that supports SVE natively, and that is the Fujitsu A64FX. So if you had access to that a machine running that hardware, then you can run native SVE code on there. But otherwise, if you have access to another ARM-based architecture like AWS Graviton 2 or ThunderX2, then you would need to run the SVE code through an emulator, either like QEMU, or ARM actually has our own which is called ARM-IE, or the ARM instruction emulator. So you can use that as well if you want to try SVE code. But as I say, SVE is coming. You will see hardware very shortly become more widely available with SVE. And as I said yesterday, the ARM, the Neoverse V1 or Zeus architecture, it's known that it will have SVE 256-bit wide SVE registers. So yeah, just to recap what we've covered so far, we've introduced the idea of vector length agnostic programming, the idea that it enables more portability with your code. You compile once, then you can run anywhere that has SVE enabled hardware. It does this by the idea of predicates. So you have, it's not just magic. It has predicate registers to be able to control this type of vectorization. The actual vector length, the L, is set by the CPU architect on the hardware. You can use a hypervisor to simulate this, to simulate a different value for this if you want, or the OS. So you could run an OS with a expecting a smaller size vector register length than the hardware if you wanted to. But essentially, you also need to bear in mind that it's multiples of 128 bits. So you've got this vector length. The total vector register length is equal to this factor len times 128. And SVE, it was designed with HPC in mind, so it does know what it's doing in terms of vectorizing complex structures and loops and other kinds of conditionals within those loops that wouldn't vectorize normally. And yeah, there's a lot of open source or work already out there that covers SVE, and also a lot of commercial tools support as well. Yeah, I'll press on a bit because I've already covered this. So I'll now go into, for the last few minutes, we'll talk about some SVE instructions. So this is like going back to what we discussed at the beginning in terms of Neon with the fixed vector register size, but now we're going to look at the SVE approach and how how it works really. So just to recap, we have what we call predicate registers. Again, we've got 16 of those. They begin with a P. So here we have register P0. Again, we're looking at 256-bit wide vectors, scalable vectors. And we have this instruction, which is a predicate instruction operating on this predicate register with a representation of doubles. So the doubles are 64-bit wide. And what this instruction is doing on this predicate register is to say that set all of the relevant bits in the predicate register to 1, so that they're true. So please note that the remaining bits in the, because it's a, essentially we have 4 lanes again here because of the data type in question, how it fits within the vector register. The remaining bits in the predicate register are ignored here. So we only need 4 bits, and those are the 4 bits spaced within each of these lanes within this predicate register. Similarly, if you were looking at single precision data, you would have 8 of these items that could fit within a vector register. So in that case, you would need 8 bit setting in the predicate register. And again, this is how it would work. So that's what it looks like for that particular instruction. A more complex instruction is the while less than predicate instruction, which is basically a counter for when these two operands are working. So there's the lower one and the upper one. So basically you have a counter that when by increments of 1 starting from this operand, when is that counter less than, note the less than this operand here. There is a while lower than variant as well, but the less than is for if these were to be signed, whereas the lower than, you don't need to worry about sign on these two values. That's all the difference is, in case you're wondering later on. But it's used to the significance of this instruction is that it's used to control loops. And I mentioned before how we've got predicate-driven loop control with SVE, and this is the key instruction where this comes in. And what we're doing here is this is just basically a loop which we'll go into in more detail, that runs from, say, the value of 8 to 11. So these are two literals, 8 and 11, stored in these 64-bit wide vector registers. Registers, non-vector. But that's irrelevant. It's just these values that are relevant, 8 and 11. So what this instruction is doing on this predicate register is that if we're representing 64-bit double precisions in our vector register, we start off, say, at this end, and what we can do is we've got, we're comparing the two operands. So we have 8 and 11. So to start off with, we say, is 11 less than 8? Because it's less than. And the answer is yes. So that's true. We move on to the next. So we're adding 1 now onto 8. So is 9 less than 11? Yes. So we put 1 there. It's true. And again, we add another 1 onto 9 this time. So it's 10. So is 10 less than 11? Yes. So we put 1 true there. We carry on. So is 11 less than 11? No. So that's false. So that's how we would fill this predicate register based on this on this loop type structure with 64 bits. If we were to move to 32 bits, it's the same kind of operation, but here we're only going to we're still running from 8 to 11, so we're still doing our increments, but we fill the three the three active bits at this end rather than straight through, because of the size of the data. That's the thing to bear in mind here. In terms of load store operations, so we've covered the while less than operation, and now we can, how do you get data actually into a predicate, into a vector register using a predicate? And that's what this example will show. So we've done what we did before. Please sort of try to imagine some values in a double precision, 64-bit values in a double precision array A. And again, we're running this loop from 8 to 11. We've set up this predicate register P0 like we did on the previous slide. And here's some example data in that A array. And we've said that it's of size, yeah, don't worry about the size. So yeah, we're basically doing that. So we have everything set up, but then how do we load up the vector register? So we're really looking at this instruction, which is to load the double word 64 bits into a vector register. Well, the way this works is that we have this predicate register. So we give the predicate register to the instruction with the location of the array with offsets, and the vector register which it needs to be loaded into and also the representation, which is double precisions here, and the predicate register. Now note there's a Z here, and I'll just cover this quickly, but what the Z means is that it means 0 on inactive lanes in the predicate register. So basically, whenever there's a 0 in a predicate register lane, it will put 0 in the resulting vector. It won't copy the value across. So this is essentially how this operation works. So acting on your predicate register with the data, these values will be copied across to the new vector register, Z0, but the last value, which is incidentally, not a number, because there's a 0, because of this Z, instead of copying across the value, it will just put a 0 into this here, into this register. The one alternative to using a Z would be M, which would be to merge the data. Now, what merging is it merges with what's already in the vector register. So if there's nothing there, then there'll be nothing there anyway. So how do you how do you count by vector width? I mean, this is a good question because, as I've said earlier, the compiler doesn't know the size of the vectors, the vector registers. So it has this very powerful instruction, IncW or IncD, and that means increase the counter by either the size of the vector length divided by 32 for words, or doubles for D. I'll now go into an example of, we'll kind of pull everything together that we've covered so far. And I'll try to go through this quickly of how you would do a conditional multiply with SVE. So we load up the predicate register with the, just quickly, we're saying each of the double precision representation lanes are true, and then using the 0 register for some here x. So x9 is the size of the loop, which will be 3 for this loop. We're just going again over a loop of size 3, loading up the data. We're moving this literal value of 1.5 into this vector register Z0, and we generated a P1 register, predicate register, based on that. So based on this loop from 0 to it's going from 0 to 2, we'd have this predicate register based on what we discussed a couple of slides ago, the while less than, but here it's while lower than. But it doesn't really matter because they're both positive values anyway. Okay, so there's your predicate register. When we do the vector register, if we look at the data, that's how it might look in memory, the value of the array. And we can do some, we can do a load based on doubles into a vector register by using the P1 predicate. As discussed before, we copy across, but because it's P1 on Z, we 0 on it in an active lane, which is there. So the last lane is inactive, so we 0 on that. So we set up a new P2 register, which just this FCMG T just means compare if greater than. So we do another predication, but this time we're using P1 on the Z vector Z1, in other words, is A or the value in the array A greater than 0. So when it's greater than 0, we put a 1 in the predicate there. We can then do a multiplication using this predicate register P2, using fmul. So it's just acting, we have a new register Z1, vector register, acting on predicate P2, using Z1 from here. And then we can store the memory, we can store the result back into memory using the store instruction. And finally, we're going to increase the loop here by the double precision type length, and we can repeat if necessary. But we can do this time on predication. So it's a much shorter loop. We don't need a drain loop like we needed before. And we can just, because P1 here will be 0 because we've used all the data, we complete. It's far more short. So this is how a loop would look using SVE, basically, with predication. So far, I've covered how you would program an SVE loop with assembly. Obviously, you don't have to do it that way. There's another level up, and that is using the ARM-C language extensions again. There's a nice header file for SVE that you can use. That gives you some very convenient data types. You can then use those data types with intrinsic functions so that you can include those in your C code, for example. And this is just an example of what it looks like. So, for a general loop there, if we were to represent this C code in terms of neon intrinsics for 128-bit neon type programming, then we can use the intrinsics like we introduced a few slides back. We also have SVE intrinsics, note, no drain loop. Just to go into more detail what this looks like. So as I've said, there's a drain loop with the neon type vectorization, but with SVE, no drain loop. And what are the intrinsics doing? Well, in terms of, I guess, assembly language, we can see here that they're doing quite a lot, but we kind of covered this loop in the previous couple of slides ago. But you can see that the intrinsic, this code, which is representing the assembly, is far more shorter than we had before. So intrinsic, if you want to use them, because you can see how well this is just giving you an idea of what assembly instructions are represented by the intrinsics. This intrinsic is doing a lot of the predication work on the loop. Basically, it's giving you a counter for your an upper bound for your loop in your C code based on assembly, which is using predication instructions. Okay, so I'm out of time, so I can't cover that in more detail, but as an overview, SVE does give you more. It's far more powerful to program because of the idea of predicates. Now, even though we've covered some assembly language and intrinsics, we really don't have to program this way. The compilers are intelligent enough to know about SVE and generating efficient loops based on predicates and so forth. So everyone's more than welcome to try compilers to do this. and then you can look at the assembly if you wish, or try to do some hand optimization with assembly and intrinsics. But as I say, the compilers are, they're very smart. And the idea is that using, predication, vector length agnostic approach, it does enable us to vectorize more parts of the code, hopefully. So yeah, it'd be great if there's any feedback, please feel free to go ahead and try emulators if you're on ARM hardware already, or even if you have access to the A64FX machines. Yeah, it'd be great to hear from anyone. So thanks very much today for listening, and I'll end this talk there.
Thanks, Phil. Any questions from anyone?
Hello, Dinesh here from Manipal. Phil, if the value of n changes in the loop, it would not affect. Would it? Semantically, it would work properly.
Yes, for in the examples, yes, n is it's irrespective. So in some of the examples, I've used n as a fixed size, but
No. I'm asking whether if the n value changes within the loop, inside the loop, I say n equal to n minus 1.
Do you mean something like recursion?
Maybe, but I just change the value of n. N is fixed. Let's say 10 earlier. Okay, at runtime, let us say it is 10. Inside the loop, I'll say n equal to 8 in between.
Okay, I see what you mean. Yes. Yeah. Well, if you were writing assembly, you'd write it to account for that. So it wouldn't necessarily be a loop. The examples are idealized in that case, that they're considering a loop structure. I'd have to think about that one. I can't really answer directly, but I see what you're thinking. Yeah, I'm thinking something like.
Yeah, I understand. Can you change the vector length at runtime? You said the operating system can change the value of the vector length.
Yeah, that's possible. Or if you're running a hypervisor, a virtual machine, or something like that, it's basically that you have you've got the vector length. Okay, that's fixed. But the idea of programming you're programming it from an agnostic approach. So the idea is that the compiler, or code writer shouldn't need to know about the vector length. But yes, you can change it.
Yeah, but if this code is running in between, okay, SVE code is running at that time, if the vector length changes in the operating system, would it affect the semantics?
Well, it wouldn't. Usually, you wouldn't be changing the size of the vector length as the code was running. It would be something that was set at you wouldn't be able to, if you were in user space within the OS, it wouldn't let you change the vector length. It would either be a boot time option or something like that.
Okay. Okay, Phil. Thank you. That's all from my side.
Thanks very much.
Hi Phil, I'm Setu I'm an undergrad at IIIT Delhi. I wanted to ask one question.
Yep.
So the predicate register which we are working with, so suppose I have a very specific data structure which might not, so suppose let's say I have a vector and I want to use some predication such that I want to just take the last, the two LSB elements as well as the two MSB elements. Now so can I explicitly load some value into predicate register? Like I have a bitmap which is known to me because like I have made the whole data structure and I know exactly which elements I want to predicate for and which I do not want to. So can I explicitly load this bitmap into my predicate register instead of doing that like x less than 5 or something like that?
Yes, yeah, there are ways of doing that. I mean, it depends. Firstly, what would be the size of your bitmap?
Right. So suppose I'm taking care of that. Let's say my each of my element of my vector is, let's say, 64 bits, and I'm using 256-bit vector length. So the bitmap would be 4 bits long. Now let's say I want to load a very specific bitmap. Let's say I just want to set the first bit, right? So I want to load 0010. So does the ISA allow me to do this explicit loading as well?
Yes, there are instructions that you could use. There are many instructions that I haven't talked about, but I can't say exactly which one it would be or which instructions, but there'd be a choice. Yeah, you could do that.
All right, thank you.
Thanks.
Phil, this is Rupesh. I have a rather curiosity question. We had this main loop and then the drain loop, and SVE is just allowing you to write it just once, and that looks a little magical, especially at the lowest level in the hardware. Is there any downside of getting this done in the hardware, or the performance-wise or power-wise, there are no issues at all?
It's all dependent. I mean, it can make it easier to get. It depends what application you're working with, really. So it's application dependent. I mean, we hope in the majority of cases that it's going to help with codes, and that having more vectorization is a good thing. But it might be that it's not in some cases. So it depends. You know the effort that it takes to do the way SVE does the loops with using predicate registers. If you're using a compiler, then different compilers will operate slightly differently. You know, some compilers will use more predicate registers because we've got you know, we can use predicate registers. Other compilers will use less. You know, that it depends what's happening, really. So there's no general yes, it's better, or no, it's not. It depends. And also it depends on the size of vector, I guess, and the type of data that you've got as well. Because it's I mean, in terms of being out there in use, we've only got the A64FX machine that has real hardware where you can, you know, try your code in reality at the moment. So, you know, experiences on that are generally pretty good for some applications, and in others, you know, it's harder to get the performance because it's just the way the code is and the type of data. So I'm sorry I can't give a direct answer, but it's just one of those things. Just try and see.
No, I do understand, and sure, I agree. Yeah, thanks a lot.
Thanks.
Any other questions on this part of the talk? All right, so looks like we are good to go to the next part.
Okay, so hopefully you can all see the next talk, which will be shorter than the previous talk. But for this talk, I'm going to talk about the work that ARM does in terms of artificial intelligence and machine learning. So it's not just focused on HPC. It will be what the company does in general, though there will be some HPC aspects as we go on. So I'll start off by talking about containers, because we all know containerization is very important to the machine learning type workflows. So it's very important to have good support for containers. And then I'll talk about machine learning and AI in terms of what developments we have from our processor line, what work we do with the community to support these applications, what libraries are available out there, and projects we have ongoing currently. And then I'll end by talking a little bit about the developments we have for machine learning and AI applications in the actual instruction set architecture, instructions that are CPU type that help AI applications. So in terms of containers, then we've worked with the Open Container Initiative for about 6 or so years now, and the aim of that group is to promote common open standards and specifications for container technology, and from our point, having that link with that group has enabled us to get a lot of support for ARM out there in the community. We've also worked with Kubernetes, who that's another open source project for running kind of containerized workloads in the cloud and other computing platforms. So we've got a lot of community support there as well, and we also work with standards and other bodies that are heavily involved with machine learning and AI applications. So we do have a very strong focus on the community for development of getting containers working on ARM hardware. One example of this is what we've done with Docker. So basically, for Docker, around, I think it was a couple of years ago, sorry, it was in 2019, yeah. We announced a strategic partnership that was the aim is to enable cloud developers to build their applications on ARM architectures, but we supported software that would enable them to do that very quickly, in minutes. So if you want to get your Docker instance running quickly, then on ARM, then it should be very easy to do that. So we did a lot of work to get that up and running. In terms of current support for Docker, I mean, Docker is just one of the containers, so I'm just mentioning that, but we have a lot of so a lot of the official images have official ARM support. So 118 out of 166 are supported for ARM architecture. So there are a lot of containers out there that you can just pull straight out that will work on an ARM architecture, be that on premises or cloud type hardware. In terms of machine learning, so what do we do in terms of supporting the community applications? Well, you might be aware of the recent MacBooks that were released the end of last year that have that they're running ARM-based processors, the M1. So we did a lot of work with TensorFlow to ensure that optimizations were released for that to work on the M1s very well. You can download GCC and Docker builds from the ARM HPC users group GitLab website, which I mentioned yesterday. We do a lot of work constantly regarding getting those application, working well on ARM architecture. There's also a GitHub release of the deep learning application, DeepBench, and ARM is actively involved with the development of that. And we've just recently, there was a blog published about 2 weeks ago, I think, on the ARM website, that we've updated our Docker images for PyTorch as well, and TensorFlow. So they've been recently updated. So a lot of work is going on with the community. In terms of what we've done for machine learning and applicability to our CPUs or CPU designs, I mean, since around 9 years ago, 2012 or so, when the Cortex A53 was announced, at that point we've added quite a lot of improvements to the processor to help capability for ML applications. I mean, in terms of, for example, more recently, the Neoverse N1 included support for half precision. So, that brought a lot of, because that type of that CPU design could support half precision, there was a big performance increase, because going from the Helios or Cortex A53 to N1, because obviously a lot of ML applications can take advantage of the lower precision aspect. So that gave a big boost. And coming next, I mean, with V1, with Zeus, we've got this predicted 25 times improvement, because not only you've not just got support for half precision, but you've got support for B-float 16, the brain float precision representation. So, and you've got the 256-bit wide vectors to deal with. So Zeus is going to bring a great performance improvement for ML applications. So certainly the evolution of the CPUs or CPU design over the last 9 or so years has meant that there's a lot of performance improvement for ML applications on ARM. So in terms of what is, I mean, for the coming years, it's obvious that we're going to have a lot more focus on instructions for on CPU ML improvements, because it will bring about a lot of help for programming ML applications. I mean, if there are more instructions available from the CPU, then surely it's going to be easier to program your ML application on that hardware. So we're aware of this, and we are introducing, as I showed yesterday, in terms of the ARM v8, going from version 0 to where we are really today. We're adding instructions all the time to support machine learning type applications. And as I said, B-float 16 was added at version 8.6. And the V1 core will support the B-float representation. So to summarize what ARM is doing for ML, we do a lot of work for the community and containers. We ensure that containers work effectively and easily on ARM hardware. We've worked on improving image classifiers. So, you know, for workloads, ML workloads, we have optimized versions of those and released them to the communities. And as we go forward, you know, we expect more features to appear on the on CPU capability in terms of instructions available, and also, you know, on the latest hardware as well. That's the hardware roadmap in the future is committed to ensuring that new designs are very suitable and very performant with ML applications. So going on now to what we do in terms of general support, because I've discussed the ecosystem in terms of what we do for the applications, the ML applications. We do, you know, a lot of work supporting the communities, developers of those, to ensure that not only do they build with the compilers, be those open source compilers or commercial compilers, but we ensure that they're optimized for running on ARM hardware, and we do work with those communities very closely to ensure all that. Furthermore, in terms of what we do on the commercial side, we have our own ARM neural net library, which is available open source. It's a software development kit, so that you can download that on Linux, and that runs on the more power efficient type ARM hardware though, so it's not really focused on HPC. And similarly, there's the ARM compute library, which is it's really a collection of low level optimized functions for the Cortex A CPU range, and also our Mali GPU for ML. So again, you can try that library. And in terms of hardware products, you're aware of most of these hardware IP designs. It's just to highlight here on this slide that we do support hardware development for ML AI applications, and there's a lot of hardware already out there in use. You know, for example, the GPU, the ARM Mali, that's used in a lot of ML processors that are in service. And on the HPC side, we've got the Neovo, which is already released, and then the V1 Zeus about to be, you know, released in the near future. So here are some links to recent work that we've been involved with, that if you'd like to look at it. It's all open source, and as I've said, we develop you know, these applications, TensorFlow, PyTorch, and ensure that they are working well on ARM hardware with ARM tools. So yeah, there's always a lot of community effort ongoing there. I mean, in general, we encourage community support. So, you know, if anyone from the ML community wishes to work with us, that's encouraged. So yeah, and anything community driven is great. As just a general overview, this is how I mean the TensorFlow software stack looks on ARM. Depending on which level you start at, underneath TensorFlow framework, we've got these several engines which are we've all colleagues have contributed to their optimized form on ARM. The Eigen library, again, that we've done optimizations for that to get it working on ARM. We can link the Eigen library with 1DNN or the ARM performance libraries, you know, to get really good performance on ARM hardware. All this has taken a lot of effort. We've had internal research projects to help leverage this forward. But yeah, it's an ongoing thing. So it's kind of work still in progress, always in progress. And this is another schematic how it all ties in. For those who are familiar with TensorFlow, in terms of the components, I mean, it's just basically going down the software stack. So at the lower level, you can link these to more optimized libraries and routines on ARM, just as easy as you could on any other architecture. So I'll keep this talk short, but in terms of what developments we have for CPU or on CPU type instructions, I've mentioned before the bfloat 16 you know, type representation. And I mean, why is this important? Well, we had capability for this released in ARM v8.6a, which was about, I guess, nearly 18 months ago, September 2019. The aim is that with bfloat 16, it's capable of speeding up most ML applications because, as you know, ML is very floating point intensive, usually that type of workload, but it doesn't matter about precision. So what bfloat 16 does is give you, it retains the range of, because it's got the same size exponent, it maintains the range of standard single precision representation, you know, in 32 bits, but you lose precision at the cost of this smaller, of the 16-bit representation. But for most ML applications, that really doesn't matter. You've still got your same range, and a little bit of loss of accuracy doesn't matter. It's not good enough to just use half precision, which has been around a while, because with half precision, you've got a smaller exponent, so greatly reduced range on your. So even though you've got more precision than you would have with the bfloat representation, you lose a lot of range. So it's really not useful for ML. So this is why the bfloat representation has been introduced. And what we've seen so far is that for architectures that are using this, we have seen good performance gains. We've also introduced instructions that you can use with vectors for Neon and SVE. So the BF dot and BF MMLA. So you've got a dot product and on CPU dot product instruction and a matrix multiply instruction. So those are both on CPU. So again, less work for the software, compiler and tools applications because the CPU has capability. So again, it's these are instructions that are dedicated to ML or the ML space. and they're both so not just these instructions, but these and others are supported very well in the ARM libraries that I mentioned, the neural network and compute libraries, if you want to look at those. So finally, just to give an idea what matrix the matrix multiply operation looks like in terms of operating on your data and your registers. It essentially allows you to do matrix multiplication in less operations. So in terms of what real world benefits this will bring is that the maths libraries should become faster, because you don't have to do as much coding. There's more capability on the CPU to do the operations more efficiently and faster, because you're not doing as many operations. Each operation is less expensive as well. So that's basically why we want these on CPU operations. So that really summarizes what I have to say in terms of ML, what we're doing for ML. So overall, a lot of work for the community or with the community to get the well-known ML applications running on ARM hardware. Most of them already are supported. You can pull Docker images ready to run directly on ARM hardware. That's very easy to do. You can build the main ML packages, TensorFlow, PyTorch, DeepBench, etc., and run those on ARM hardware. And also not just on the software and application side, but on the hardware side, we've constantly added on CPU instructions that are dedicated to ML AI applications, so that the CPU can do more work, and that is an ongoing process. So over the coming years, as we see more ARM-based hardware, you'll see more on CPU instructions being added for ML and AI. Okay, so I can end there, and please, if anyone has any questions, please ask. And thank you very much again for listening. Thanks.
Thanks, Phil. Any questions on this part or any earlier part of the talk as well? Feel free.
Yeah, Dinesh here once again from Manipal. The cost of the servers are slightly high, I think, because most of the in our university, most of the complaints come from machine learning, saying that all software or whatever systems that we have is inadequate to run machine learning problems. It takes sometimes 5 days, a week or so. And we have a few desktops around here, maybe 200 desktops we have. So to invest about 20 lakh Indian rupees is expensive for a server. So do you have any solution to merge the available desktops to run machine learning on heterogeneous computers? I'm just asking, would we have different desktops? Is there any way in which we can use them for high performance computing? Simple ways?
So I guess that you don't really need a fast interconnect, or do you? Because I don't really know about, I don't know the workload in great detail. But if you were to merge desktops, then it's possible. But what CPUs are the desktops running?
Intel as well as ARM we have. So it may not be a wise decision to invest on a high performance computer right now. It costs in Indian rupees, costs about 15 to 20 lakhs to run a reasonably big machine learning application. So just looking at options, is it wise to invest on a server which runs all these TensorFlow, etc., whatever, PyTorch, etc., which needs high-end computing? So,
can I ask as well, for your desktops, what ARM hardware are they running?
not sure. Majority of them are Intel processors. So,
Okay.
okay.
Well, one suggestion would be: have you tried any cloud resources for your workloads at all?
I didn't get it. Please repeat.
Have you tried using any cloud resource?
Yes, we have also. We have stitched up an OpenStack private cloud out here, trying to merge the resources. Still, we are not getting performance out here.
Okay. Can I ask what processors have you used on the cloud? Because I'm just thinking that, you know, that there are cloud offerings now of ARM-based hardware, and usually it's competitively priced against Intel. And you know that most of them are based on Neoverse N1 at this moment. So it might be worth just trying cloud and seeing what the workload is like on there. You know, the AWS Graviton 2 is a good, processor to look at first. You know, you've also got the Ampere Ultra, that type of cloud resource, or even an older processor from, you know, AWS. The Graviton 1 may be okay.
Yeah,
I'm just thinking price.
The problem here is that we can't ask our students to go for a cloud. They have to pay on their own, right? So that is a flexible amount. We don't know how much budget to be associated with cloud resources. As an institute, I'm talking about an institute. So who pays for the cloud? Is it the students or the institute? So I'm just trying to resolve that problem by seeing if we can offer those high performance computing without extra investment.
Okay. Well, I'm not the best person to answer this question, but I can put you in contact with a colleague who would know the right way of going about this.
Okay, fine.
Certainly, that would be the thing for me to do, because I mean, I think in principle, it should be possible for the university to get some arrangement, I would expect, but I don't know the details of how you would do that or what sort of price it would be, because I'm only comparing with what happens in the UK. You know, I know in the UK that there are setups like that, but I can certainly, you know, it's certainly an option, but I mean, some of the workloads I've seen on cloud resources are pretty good in terms of cost. You know, the cloud is becoming more, you know, professional rather than, you know, running on a desk or something like that. And in terms of cost as well. But then again, you know, on the other hand, you might like to keep your desktop, and there might be a solution there as well. But certainly, yeah, it's an interesting question.
Okay, thank you, Phil.
Hello, Phil. Hello, Phil. Am I Mitul Nagar here?
Hi.
Hello, sir. In this slide, what is they multiply 2x2 matrix only? So, is it possible to have a higher size of matrix to be multiplied?
That's a good question. Good question. So it depends on how much you could fit into the vector register, I guess, and what your representation is. So I think here the example you're looking at either, you know, single precision. So with single precision, you would, be looking at the 4, I guess, in a 1 to 8-bit wide vector, you've got 4. So that's why you'd have your 2 by 2 matrix. So you can't really get any more than that, I guess, here. Yeah.
Okay. Okay, sir. And one more thing, that is there any instruction that that would help the entire machine learning or CNN the flow, like ReLU and any other? Is there any instruction that supported by this process?
I don't know one off the top of my head. I'm sorry. It's possible, but I really can't answer.
Okay, fine, sir.
If it's not available now, more than likely it will be in the future.
Okay, because why I ask, because it will accelerate the machine learning more. That's why I ask.
Yeah. As I say, I just check. Please check the website, because it's possible. Yeah.
Okay, sir. Okay.
Hi, Phil.
Sir?
Hi, Phil. This is Amit Mankori here.
Hi.
I have a question. Hi, I have a question regarding Cortex-M CPUs with machine learning. So I've tried, some of the tools that you mentioned about the machine learning on Cortex-A processors. But do you know if any good machine learning, tools or framework available for Cortex-M boards? Because we are going towards the edge computing, and the edge computing will require a lot of MLs on the edge devices rather than on the larger machines. So do you know of any framework that we can use with Cortex-M?
Is it possible to use our NN library on Cortex-M? Have you tried that? Because I think it works on Cortex-M.
ARM NN, you mean?
Yes.
Okay, I haven't tried that. I'll try that.
Okay. Yeah, I think so.
Excuse me, sir. This is Gitanshu from COEP College. I'm an postgraduate student. I was actually searching about on the website, and also I was thinking about the machine learning, this ARM processor that can be used in a automobile for an ADAS system, machine learning based or AI based ADAS system, or a cruise control system. Is it possible for me to use these microcontrollers that you have mentioned, that can also certified at ISO 26262 guidelines as well as MAP guidelines accordingly in the automobile, sir?
I must admit I'm not knowledgeable of the automotive industry. But did you say you have looked on the ARM website?
Yes, sir. Yes, sir. Actually, I wasn't getting a proper idea that could be used there to implement these guidelines accordingly and use the same AI and ML algorithm for these kinds of system in a modern car, electric car, actually.
Okay. Off the top of my head, I'd guess it's possible, but I wouldn't know how to go about it, because I'm aware that a lot of our technology is used in that kind of automotive area. But I wouldn't know how to go about finding out the exactly what is. I know, for example, we have we do work with a lot of motor manufacturers to get this technology in use in vehicles.
Actually, for AI and ML, we all know like it requires a large amount of data, and in a car we have some very limited amount and very limited resource. So what kind of stuff that you can suggest, what kind of product that you can suggest me to use there actually for implementing an AI or an ML algorithm or ML program for this ADAS or a cruise control system, sir?
Okay, so is it cruise control that you're particularly interested in?
Sir, actually, I'm interested in both ADAS and cruise control. Any would be for me is plausible. Like I can, we can implement it, but majorly based on automobiles, sir.
Okay, is it possible for you to send me an email, and then I'll chase this up internally, because it's really
Sure,
not my area, but that would be the best course of action, and we can get an answer back to you that way.
Sure, sir. Sure, sir. Will share. Please, can you share your email ID, or sir would share? No problem. Any
Yes,
would be
yeah,
anything.
it's
Yeah, I
on
can.
the slide.
Sure, sir. Thank you very much, sir.
Okay, thanks. I'm sure Rupesh will publish the slides on the website, so my email will be on there. Thanks.
Thank you very
I'll
much,
do
sir.
that. Any other questions?
Yeah, hello, sir. This is Anbu Selvi from Chennai, SSM College of Engineering. I heard about process which are used in ML-based applications. Like I found ethos N-series process that are used for ML, and so what could be the important features that, as you listed, neon and all, right? How far this ethos is suitable for MI-based applications?
It really depends what the workload looks like. All we can suggest is to just try the workload on the processor. You know, the neon based architecture is capable, you know, for ML workloads. But then without the I guess the bfloat 16, some ML workloads cannot do so well. So I'm hesitant to say this works or this doesn't. You know, that's the problem. I just recommend trying different architectures. You know, whatever happens, the newer architectures that are coming shortly should see a lot of improvement. So I'd recommend looking out for Zeus or V1. So when the Neoverse V1 is released, please, you know, consider that and have a look. If you're able to wait a while.
Thank you, sir.
Thanks.
Hello, am I audible?
Yeah, go ahead.
So I'm Mayank. I'm an undergrad from Triple ITT. So I just had one question about this high performance matrix multiplication. So since we are only doing a matrix multiplication of 2 cross 2, why don't rather than implementing and using this, we basically have a external or a basically you can say a co-processor type of thing which is doing which can basically do much larger matrix multiplications or all the vector, so not the vector but the matrix multiplication stuff, because I think it might basically, if we are doing it, it is of course increasing the complexity of the chip itself, but at that point, if I'm using math libraries on the top, so it should not matter, right? If I am using a co-processor or using the internal 2 cross 2 multiplication. So is this a viable thing to do, or is there a reason why we have done it in a basically 2 cross 2 multiplication inside the processor itself?
That's a good question. Really, it just depends on what hardware you have at the time and your application, because these on CPU instructions, like the FMMLA for the the matrix multiplication, Basically, you know, if you're using a particular, say an embedded processor, you might not have the you might be glad of it because you wouldn't have access to a coprocessor or something like that, you know. But if you're able to offload the work onto a GPU or something like that, then you probably don't need to worry about this situation. These instructions are just something that we're introducing because we cover a lot of different applications areas, and you know that they have to be applicable to that particular type of hardware, if that makes sense. So it's really whatever hardware you've got hold of, where you're running your application, and it's whatever you're getting at the time.
So thank you for that answer. So just to make sure, so since we need some, you can say, basic implementation, so we can write libraries around it, which can be ported to multiple, you can say, implementations, which might have other coprocessors or not. So this is only for that purpose, right? If I have a coprocessor, that would be better to use in some cases if we have large amounts of data, if I do not want to do, let's say, matrix multiplications on this.
Yes, exactly. It depends where you're capturing the data or where you're running the application. If it's on a mobile phone or something, then you're going to be grateful of the on CPU support. But if you're in a data center with your co-processors, lots of HPC resource, then you probably don't need to worry because you can let the libraries run somewhere and get the result that way. Yeah.
Thank you.
Hello, sir. Sir, I am Saurabh Khanna. Sir, what is the application of this ARM-based HPC?
Sorry. Can I ask you to repeat the question?
Hello, sir.
Oh, hello. Hi.
Sir,
Are you able to repeat the question, please?
Sir, what is the application of this ARM-based HPC?
I not really understand. Do you mean the application of ARM-based HPC? I think
What,
that
what is the application of ARM-based HPC?
Okay, so it's a general term. ARM in HPC, is that what you're asking? We cover lots of HPC hardware, tools, applications, or do you have any more specific questions to ask?
Any other final questions? All right. So that brings us to the end of this 2-day workshop from ARM on ARM-based HPC. And I would like to thank Phil a lot for sparing his time and experience for us. It was difficult. I mean, I must say that the number of things that ARM does seems to be quite large. And it must have been very difficult for Phil to cover all of that. But I think ARM is a versatile company, and like the pizza-based example that Phil gave yesterday, And I think Phil has succeeded in bringing in that versatility in his talk, where he had covered not only in breadth about different topics, but also went in depth about, for example, in vectorization and SVE, all the way to the predication and assembly code. So I must say it was a difficult balancing act for Phil, but I think he has executed it very well. And I'm very thankful to Phil as well as ARM for giving us this guidance on various ARM architectures, as well as different software tools, as well as its use in different libraries, compilers, etc. I would also like to thank Apurva Verma from ARM for coordinating all this effort. She has been there in the discussions all throughout, and she is the primary coordinator from ARM for this effort. On behalf of various nodal centers and CDAC, that is Ashish Koelkar from CDAC, Professor Sharad Sinha from IIT Goa, Sandeep Chandran from IIT Palakkad, and Somnath Roy from IIT Kharagpur, as well as myself from IIT Madras. I would like to thank all of you for this very nice effort, which allowed us to reach a lot of people who are working in HPC, and some of the attendees were not only from India, but also from various other countries. I would also like to thank all the participants for your active participation. I think the interaction was very nice. Some of the questions were really very good. And on behalf of the whole team, I would like to thank all the participants as well as Phil once again. So that brings us to the end of this session. Thanks a lot.
Thank you very much, everyone, and thanks for letting
Thank you.
us. Thank you. Bye.
Thank you, everyone. Bye.